Hi, welcome back to the lecture on a practical guide to quantitative finance interviews. This is going to be our next lecture, and we're going to talk about combinatorial analysis. So combinatorial analysis seems to be a fancy name, but the only thing it denotes is counting. And the basic principle is counting is that if we denote S to be a set of length k sequences, like here, and if there are n1 possible first entries and n2 possible second entries for each first entries, which is conditional on the first entry equal to something from n1, okay? And we also need to have n3 possible third entries conditional on our choice of the first and second entries, and etc. Then there are going to be a total of the multiplication of all these possible counts, and it is going to be the value of our possible outcomes. So there are mainly two kinds of combinatorial counting that requires us to analysis. So the first one is permutation. It's a kind of rearrangement of objectives into distinctive sequences. So, which means if there are n objectives, let's say if we have like 10 balls, well, we have 3 red, 2 blue, and 5 green. And there are total how many ways of permutation? To put them differently, there are 10 factorial divided by 3 factorial, 2 factorial, and 5 factorial, right? It's like that. And what does it makes different is because the order matters, okay? The order matters. But for combinations, the order doesn't matter. We only need to pick the number R things, objectives from the total n samples, okay? So the difference now becomes n factorial divided by r factorial but we have one more n minus r factorial, right? And this extra item is actually the thing that's related to that the order doesn't matter, because so we need to cancel out the effect of order brings on us, which means there are less different ways of combination, right? And this is a binomial theorem. We are going to talk about it later in one of our sample questions. Just remember it is quite important because x plus y to the power of n is a kind of polynomial which we frequently meet, right? Which frequently see. And it links a polynomial with what? With a combination. Basically with a counting. And last but not least, there is also another important one is the inclusion-exclusion principle. So basically, the probability of having both or having one from event A and event 2 is going to be the sum of these two events individually and minus the probability that they happen together, right? And this could be expanded to our general cases. And the permutation here is going to have n r items, okay? And now let's come to our sample questions today. So the first question, poker hands. What are the probabilities of getting hands with 4 of a kind, 4 of the 5 cards with the same value, hands with a full house, and the hands with 2 pieces? So first of the thing is that poker in English doesn't mean 斗地主 or any other kind of poker games in China, okay? Poker only means Texas Hold'em, right? The most famous card game in this world. And it is also a kind of after school activity for all the quant analysts. So 4 of the kind is basically, you are going to find 4 of the 5 cards with the same value. So we have all the way from A to all the way to what? 10 and J, K, J, Q, K. In total, there are 13 different kinds of cards, right? So jokers are excluded. Okay, I excluded. So how many kinds do we have? We have 13, right? And we can pick one from any one from them. And if we pick one, then we know all four of that is going to be the same with that. And for the, because each time we need to pick out 5 cards, and you already know like 4 of them is the same, then how many choices for the last one? We still have 52 minus 4, which is 48, right? So in total, we have 13 multiplied by 48 ways to find that. And this is going to be our numerator. And what's our denominator? The denominator is just 52, 5, right? So this is going to be the answer of our first question. And for the second sub question, it's about hands with a full house. So for full house, we need to pick 3 cards of one value. Again, we have 13 choices. And within each choices, because there are 4 cards of the same number, right? So we only need 3 from them. So that is a 4-3 combination. And for the rest 2 cards, it also needs to be the same number. So we need to pick another 12, and among them there is a 4-2 choices. And again, this is the numerator, the denominator is the same, which is 52, 5. Okay. And then how about the last question? For the last question, it's a hands with the 2 pairs. So again, we know the denominator is the same, right? It's still 52 and 5. But how about the numerator? The numerator this time is that we need to first find two different numbers, and each of them is going to form a pair. So we need to first pick 2 out of the 13 different numbers from A to K, right? And then among each of them, we only need to pick 2 out of the 4 because we have the cube, we have the flaxseed, and we have the diamond, and we also, yeah, and basically we have those 4 colors. And so there are 2 pairs. So we have 2, 4, 2 combination. And how about the last choice? We still have the last choice. Is the last choice still 48 like the first question? No, okay, no. So in this here, it should be 44. Why did this case? Because after we excluded the 4 cards we have already chosen, the other 2 cards from each of these 2 pairs cannot be chosen again. So we need to minus another 4. So this is going to be 44 here. So must be careful about that. And all these ratios are quite important in the Texas Hold'em games, because if you are a mathematician, the way you play the Texas Hold'em is to calculate the difference between your odds and the probability of winning, right? And so you basically are calculating some kind of probabilities and compare them with the holders that you already have. And now let's come to our next question, which is also a classic one. So this is called hopping rabbit, but I think it has a lot of different kinds of other names. So rabbit sits at the bottom of the staircase with n stairs, okay? So the rabbit can hop up only 1 or 2 stairs at a time. So how many different ways are there for the rabbit to ascend to the top of the stairs? So let's start with a simple case. Again, for a complex question like that, where we have n values, we just start with the case where n equal to 1. Then how many choices do we have? Number of choices. We only have 1 choice, right? And how about when n equals to 2? Then we can go 1 step at one time, and we need to have 2 times to reach the second level. And we can also hop up 2 stairs at a time, right? So in total, we have 2 choices. And how about when n equals to 3? When n equals to 3, we can go like 1, 2, or what? 2, 1, or 1, 1, 1. So in total, we have 3 choices. And what about 4? We have seen some kind of pattern here, but we need to go further to check it. When n equals to 4, again, you have 1, 1, 1, 1, or 2, 2, or 1, 2, 2, or 2, 1, 2, or 1, 2, 2, right? So in total, we have 5 choices. And what can we see? We can find that the fn plus 2 if we call it Fn is the number of choices, Fn plus 2 equals to Fn plus 1 plus Fn. So this is what? This is a Fibonacci sequence. So how many ways are there for a rabbit to ascend to the top of stairs? Then we just need to do the recursion of a Fibonacci sequence, which is going to have Fn equals to Fn minus 2 plus Fn minus 1. And we can write Python or C++, any kind of coding language script to solve this problem, right? And besides, may I ask what's the complexity of a Fibonacci sequence? Well, you may guess about that. Think about it, because each time we are going to separate them into two new functions, right? So by the principle of the master law, Tn is going to be Tn minus 1 plus Tn minus 2. And this division itself only takes the complexity of 1. And in total, this is going to give us O2 to the power of n, right? Because this time we are going to have 2 of that more, okay? So this is going to be the complexity, which is a further question, which is a follow-up question. And now we come to the next one. Our old friend, the screwy pirates, they come again. So we have met them in our first chapter of Green Teaser, but now again, it comes up again. They go on for more looting and expands the group to 11 pirates. So to protect their hard-won treasure, they gather together to put all the loot in a safe. Still being a democratic bunch, which is quite interesting. Huh? So they decide that only a majority, or any majority of them, together can open the safe. So they ask a locksmith to put a certain number of locks on the safe. So to access the treasure, every lock needs to be opened. And each lock can have multiple keys, but each key only opens one lock. So the locksmith can give more than one key to each pirate. Okay, they can give more than one key. And what is the smallest number of locks need? And how many keys must each pirate carry? So the key lies is that how to think about this question. The key is that for any majority, as long as there is a group of six, they can open it, right? But a group of 5, they cannot open. So, which means for any of a group of 5 people, they should not have the ability to open that lock, right? So there must be a special lock which is targeting this 5 people group for any 5 people group. So in total, there are 11 pirates, and we're going to separate it into 5 people, and we are going to choose 5 people from them. And how many ways can we have? We're going to have 11 factorial, 5 factorial, 6 factorial. In total, this is going to be 462. And this should be the total number of locks, because we need each lock to targeting one special 5 people group, okay? And for this group, it should have how many keys? It should have 6 keys, okay? So it should require 6 keys to open it. And it should be belongs to a 6-member subgroup. So in total, we are going to have 462 locks multiplied by 6 keys and divided by 11, which is going to be 252 keys per parrot, okay? Yeah, it's a large bunch of keys. And this actually gives us some, it actually reminds us of something. You see, if we want to prevent anyone of 5 people from opening up the chest, the cost is super high, right? Which means the fairness actually brings a high cost to any of the people who want to sustain it or maintain it. And you can see now why monopoly or bankruptcy, not bankruptcy, why corruption becomes so common in our world, right? And now let's come to the next one, the chess tournament question. So the chess tournament is where it has 2n players in total, with skills 1 larger than 2, larger than 2n. So basically, this is the best one. This is the worst one. And this one may be 战赢, right? Okay, it's just a joke for Bilibili followers, okay? And it is organized as a knockout tournament so that after each round, only the winner proceeds to the next round, except for the final opponents in each round are drawn at random. So let's also assume that when 2 players meet in a game, the player with better skills always wins. What's the probability that player 1 and 2 will meet in the final? So let's first try the normal way to solve this question. Let's think it one round by another round. So let's first think about the first round. So for first round, there are in total 2n players, and the probability 1 not meet 2 in the first round is going to be what? It's going to be 2n minus 1, 2n minus 2, right? Because there are, except from the first player, there are 2n minus 1 players left. And among them, as long as it's not players 2, then it's fine, right? So this is the probability. And how about the second round? In the second round, because we are going to, there will be only 2n minus 1 people left, right? Half of them have dropped out. And so now the probability 1 not meet 2 becomes 1. Becomes to like among the 2n minus 1 people, exclude the first player. So there should be 2n minus 1 minus 2 people, right? And you can see the trick here actually. So we have, for the third round, it's going to be 2n minus 2 minus 1, 2n minus 2 minus 1. So the total probability is going to be what? It's going to be 2n minus 1, 2n minus 2, multiplied by 2n minus 1 minus 1, 2n minus 1 minus 2, multiplied by all the way to what? To 2 minus 1 and 2 minus 2, right? And you can see this part can be rewritten as 2n minus 1 minus 1. So this part is canceled out. And this should be canceled out with this 2 all the way here. And this should be 2n minus 1. And this is going to be what? Yeah, this is going to be 2n minus 1. Right? So because there are only 2n minus 1 here because this is 0, right? This does not count. So we are not going to have this one here, okay? So there are only 2n minus 1. But this is actually not the most simple way to solve this question. So if you think about it, the first player is the best, okay? And the second player is the second best. And if we want them to meet only at the last round, the only possibility is that in the first round, they are going to be separated into 2 groups, right? So there are 2n people. In group A, there is going to be 2n minus 1 people. And in group B, there should be 2n minus 1 people as well. So as long as if 1 and 2 are in the same group, they cannot meet each other in the last round, right? Because the first player must stand out from this subgroup, and his opponent in the last round must come from another group. So the only way that this could happen is that when we chosen the players in group B, if we assume player 1 is in group A, then what's the probability that the second player is in group B? Then which means among the all 2n-1 players left, exclude this first player, there is 2n-1 probability that the second player is in this group. And we have already solved the question just by the principle of counting. And this is much more convenient, okay? So now let's come to our next question, which is application letters. So you are sending job applications to find firms. Of course, you need to send out more in the real world, like around 100, I think. So Morgan Stanley, Lehman Brothers, okay, this one has gone. Maybe we replace it as well. Let's say BNP Paris, okay? Okay, I like BNP Paris. So UBS, Goldman Sachs, and Merrill Lynch. Okay, this is not called Merrill Lynch anymore. This is called BAMO. So you can see this book is quite old. So you have 5 envelopes on the table, neatly typed with names and addresses of people at these 5 firms. And you ever have 5 cover letters personalized to each of these firms. And your 3-year-old tried to be helpful and stuffed each cover letter into each of the envelopes for you. Unfortunately, she randomly put letters into envelopes without realizing that the letters are personalized. And what's the probability that all 5 cover letters are mailed to the wrong firm? So the probability all 5 wrong is hard to find, right? We can find what? We can find the probability of what? At least 1 correct. Why is that the case? Because for this thing, we can simply apply the principle of inclusion-exclusion principle, okay? Which is here. So we just need to apply this one. Probability at least 1 equals to what? Equal to sum of probability E1 minus the sum of probability E1, E2 multiplied by N2 by phi 2 plus what? Plus phi 3 probability E1, E2, E3 and minus phi 4 probability E1, E2, E3, E4 and plus what? Phi probability E1, E5. So for this E1, event 1 equals to that the first letter is correct, okay? And we can see PE1 actually is simple, it's just 1/5. And how about PE1, E2? It's just 1/5 multiplied by 1/4, right? Because after I have put 1 cover letters into 1 envelope, then there are only 4 cover letters left. And this should be 1/5 multiplied by 1/4 multiplied by 1/3. And this is the same for that. And this should be what? This should be 5 factorial. So this should be 5/4 multiplied by 5/3, 5/3, and this is 1/2, okay? And after we calculated that, we can actually finding that this is going to be this is going to be 19/30, okay? And now our answer is what? It's 11/30. And we solve out this question. And now let's come to our next problem, which I think is a little bit hard. 100th digit. So what's the 100th digit to the right of the decimal point in the decimal representation of 1 plus square root 2 to the power of 3000? I mean, it seems like a hard question where you cannot address anything from this question, right? So what information can we have? Nothing. But what's special is about this format. This is what? This is x plus y equal to n format. And do we still remember the binomial formula, the binomial theorem? This one here. So now let's write it down. So this is going to be sum of k equal to 0 to n, nk, xk, yn minus k, right? Okay, let me confirm. I didn't write anything wrong. Yeah, we are good. So let's put this in here. So 1 plus square root 2, 3000 is going to be sum of k equal to 0 to 3000, 3000 chosen k, and x is what? X is just a 1, right? So 1's k must be 1. So we'll need to take care of about the square root 2, 3000 minus k. And what can we see? The thing we can see here is that as long as this one can be, if it modulo 2 equal to 0, if this number modulo 2 equal to 0, then this is going to be an integer, right? This is going to be an integer because this one must be an integer. And then this one is going to be the same because as long as we have a 2, then it can be separated as 2, and this is 3000 minus k divided by 2, and this is going to be 2, right? So this is going to be an integer. And what does this helps us? We can see if it is 1 minus square root 3000, then what is going to be here? This is going to be negative, right? And now if this number is odd, this is going to be negative of the thing from here. So if I sum, if I call it this 1 and this is 2, if I take 1 plus 2, then all the odd items is going to be canceled out. So 1 plus square root 2n plus 1 minus square root 2n will always be an integer. Because after we take the sum, the only thing left here is all the even components, even k components. And for every even k which called modulo 2 equal to 0, it is going to be an integer. And so, because we know 1 minus square root 2 over 3000 is going to be super small, which you can find is much smaller than tens over 100, right? Because we want to check the 100th digit. Because this is super small, this is going to be less than this number, and this is an integer. So we are actually calculating 1 plus square root 2n minus plus 1 minus square root n, and then minus 1 minus square root 2n. This is going to be much smaller than tens negative 100, and which means the last decimal is going to be 0.000, where we are going to have 100 of them 1. So the last decimal must be what? Must be 9. Okay, so the last decimal must be 9. So the last digit. And now let's come to the last but not, the second last question, the birthday problem. So how many people do we need in a class to make the probability that 2 people have the same birthday more than 1/2. So we just assume 365 days a year. Well, so for each people, so the first people, it could be any day, right? It could be any day. So basically, for the first people, we can choose any one of them. But if I want the two people have the same birthday more than 1/2, how many people do we have? We need to convert them into a counting problem. And what kind of counting problem is that? So do we need to make at least have more than 1/2, right? Then we want the maximum people to have different, the probability of maximum people to have different birthday is going to be less than 1/2 because we want more than 1/2 to have the same birthday. Then it is the inverse part. And what is this? Then for each of them, the first one is going to be, we can pick any day, but how about the second one? Then because we have chosen one from that, we can only choose what, 364 for the second people. And for the third people, there are only 363 choices left. And all the way, we can put it as what? 365 nth power. And this is 365 multiplied by 364 all the way to 365 minus n plus 1, right? And we want this to be less than 1/2. And by calculating, actually, you can see this n is going to be 23. So which means this is going to be 22. And then we only need 23 people to make that happen. Okay, and this is quite interesting because you can see we only need such a small number of people, then we can make the probability of having two people having the same birthday to be larger than 1/2, right? Quite counterintuitive. And now let's come to our last question. So the last question is about the cubic of integer. So let x be an integer between 1 and 10 to the power of 12. What is the probability that the cubic of x ends with 11? So my advice is that for any question related with the digit or with the digit's value, we write this x as something in, for example, if it is 11, then we write it 10 multiplied by 1 plus 1, right? So we write according to their digit. Okay. And in this question, because it is asking us the cubic of x ends with 11. So the only thing matters with us is what? Is the last two digits of x. So let's denote it as x equal to something plus 10a plus b. Well, this is the decimal value. This is the last digit. Okay. Then x to the power of 3 for the last value is going to be what? 10a plus b to the power of 3, which is going to be b cubist to the power of 3 plus what? 330a squared b plus 30 b squared a plus 1000 a to the power of 3. And you can see the unit digit only depends on this b3 here. So this b must be 1, right? And since b must be 1, the other part becomes what? 30a2 plus 30a plus 1000 a to the power of 3. And what's the decimal value? The decimal value will only be related with 3a plus 3 multiplied by a squared, right? And then we must have this 3a ends in 1, okay? And the only choice we can have is that we need to have a equal to 7. Okay, so because we need to something multiply it, it needs to be 1. And so this is going to be the end of today's lecture. Next time we are going to talking about the conditional probability and Bayes formula. So thank you for watching. It's a long lecture and see you next time.